In the previous chapter, we were talking about electrostatics. In this, we are talking about electric current. So the difference is, see, in static, in electrostatics, in basically electrostatics, statics, we had basically nothing but electro means charges, and statics means at rest. So the charges were at rest. Their average velocity, their average velocity was basically zero. It's not that the charges were having no speed. They might be having speed, but they might be colliding here and there, and on an average, their net velocity, average velocity, average displacement, everything was zero. But in current means flow of charges. So when you talk about electric current, electric current, it is the same as saying it is electrodynamics. It is the same as saying it is electrodynamics. And dynamics is motion. So basically, we are talking about the charges in dynamics means motion, charges in motion. So because of which you will see that their average velocity will not be zero. The charges will be moving one way, one side or the other, this way, that way, and that will make up the electric current. So if you see over here, how do I define electric current? If you see over here, how I define electric current, if there is a wire, if there is a conductor, you take a cross section always for defining electric current, and you see how much charge passes that cross section, passes or crosses that cross section. You demarcate, okay, this is my area. How much charge flows through that cross section? That charge per unit time. So in 1 second, how many coulombs flows defines the current. So electric current is the rate of the flow of the charge, is the rate of the flow of a charge through a section, through through a section, through a section. So strictly speaking, current is nothing but how much charge that will flow divided by the time, divided by the time. If you ask me what is the unit, well, current itself is a fundamental quantity. Remember, units and dimensions chapter, charge is not a fundamental quantity, current is a fundamental quantity. So it's a fundamental quantity. It's a fundamental quantity having the dimensions of A, right? The SI unit, the SI unit, the SI unit is basically an ampere. SI unit is basically an ampere, and an ampere is nothing but when 1 coulomb of charge is going in 1 second. 1 coulomb of charge is going in a second. That's when you call it as an ampere. The current that you receive in your daily household is in milliamperes for most of the electrical appliances, but for heavy appliances like a heater, a hair dryer, or the AC, or the big equipments, it will be in 5 amperes or 10 amperes and such ranges. So for small equipments like your mobile chargers, it will be in few milliamperes, and in heavy equipments, it will be in the range of 5 to 15 amperes. So that gives you an idea of what an ampere is exactly. Okay, SI unit is ampere, which is coulomb per second. Great. Another thing is that it is a scalar quantity, although it has a direction. It is a scalar even if it has direction. Even if it has direction. Even if it has direction. Because it does not obey the rules of vector addition. So if it does not obey how vectors are added using triangle parallelogram laws, it's obviously not going to be a vector. Okay. Now, you might also wonder what is the direction of the current. Well, see, if the positive charges are going this way, current is in the direction of the positive charges. But if the negative charges are going this way, It's like saying positivity is going that way. It's like saying I am becoming more negative means I am losing out on the positivity, or my negativity is going away means positivity is coming inside of me. So same way, if negativity is going this way, it's like saying positivity is going that way. So current's direction is always the flow of where the positivity is going. So this is also quite important. The direction of current is the same as the flow of positivity wherever it positivity is going, that's the direction of the current. So like you can see over here, current is going to be this way, and you can see over here negative is going over here. So that's why the current direction will be towards your right hand side. Let me give you some examples related to this. Say I tell you, listen boys, there is one wire I take, and there is some cross section that I take over here. And what happens is I find out that some charges are going here, some charges are going here. Here, maybe plus 7 coulombs of charge goes, maybe here minus 3 coulombs of charge goes. And all of this happens in, let's say, 2 seconds. Can you figure out how much current is flowing? Can you figure out how much current is flowing in this particular situation? 7 coulombs of charge goes here, minus 3 charge goes over here. So total current flowing through that cross section is asked. Let me think. By definition, current is how much is the net charge flow upon the time taken. Now, if you notice, 7 coulombs of charge has gone here. Well, so charge flown is 7 for sure. But apart from that, negative 3 going here is the same as saying plus 3 has gone there. An extra plus 3 has gone there. So if I've taken out negative 3, it's as good as saying I have added positive 3 on the other side. So I can say this is also plus 3 and the whole thing divided by 2, which is 10 by 2, which is nothing but 5 amperes. So the current flowing in this wire is 5 amperes. Everybody understood this? Why this negative 3 has to be counted the other way around? Yeah, very simple. Negative 3 has gone here. So negativity has gone here. That means positivity of plus 3 has gone this side. So apart from that, extra positivity of plus 5, plus 7 also went. So plus 7 plus 3 makes it plus 10. Plus 10 by 2 is 5. Is that right? Very good. Awesome. Great. Now, whenever you have charges which are crossing a cross section, it is very easy to measure. You can say that the current which flows is the total charge which is flowing per unit time. The charge which flows will be number of the charge carriers into E divided by time, because the charges which will move will be either electrons or protons, and each electron or a proton will be having a charge of 1.6 10 to the power negative 19 coulombs. So N into E will give me the total charge. So current will be NE divided by T. Often you call this number N by T separately, and this number is nothing but number of charges flowing per unit time, per unit time, per unit time. Just to give you an example over here, if the current is, let's say, 3.2 amperes, if the current is, let's say, 3.2 amperes, we can find how many electrons or charges, particles which are carrying charges, are crossing that cross section. Just substitute it over here. You will see 3.2 is equal to N by T multiplied by E. E is nothing but 1.6 into 10 to the power minus 19. So therefore, N by T is equal to, you will have 3.2 divided by 1.6 over here, and minus 19 on the other side will become plus 19. So 3.2 by 1.6, that is nothing but 2. So 2 into 10 to the power 19. So what does this tell you? These many electrons are crossing in 1 second. Believe it. Just imagine just a simple current of 3.2 amperes, not very big, not very small, means, around 10 to the power 19, 2 into charges are crossing every second through that wire. It's just that you don't see it, but that is what is happening. Okay, it's a huge number, but each charge is extremely, extremely small. Yeah, great. Awesome. Welcome, Akshu. Welcome, everyone. Yes, yes, correct, Rama. Perfecto. Moving ahead, sir, please come to Vishakhapatnam. Oh, definitely, I would love to, man. That is a one destination I want to come. Last year I couldn't make it to Vishakhapatnam, but this year really, I want all the fans and all the students from Vishakhapatnam to assemble and post it in the comments. Sir, we want you. We'll definitely make it a point to visit. Yeah, it's all depending on your form filling, guys. That's it. Okay, current due to rotation motion of a charge. Now, sometimes you might have an atom in which an electron is revolving, or maybe just a charge for some reason is revolving. So a charge which is revolving in an orbit, in a path, circular path, is like saying there is a circular wire and in that there is a current which is flowing in it, because charge rotating or a current with charges inside it rotating is one and the same thing. So current due to rotation motion of a charge means that when you have a rotating a rotating charge, it is the same as saying there is a current loop. There is a current, loop over there. How much is that current? That current is how much charge will flow per unit time. Now let's say the charge which is moving around it is having a charge of capital or small q. So the charge which will go, let's say, is q. But let's say now that charge passes through this cross section once. By the time it again crosses, a time period of revolution will be over. So this t happens to be the time period of revolution. This is nothing but the time period of revolution or rotation, which is nothing but 2 pi by omega, where omega is nothing but your angular speed, circular motion concept. Omega is angular speed, which is also there in SHM. T is 2 pi by omega, very similar. So therefore, current will be nothing but Q by 2 pi by omega. Omega goes on the top, so it will become Q omega divided by 2 pi. So that is what you are going to get. So current will be Q omega divided by 2 pi. Is this absolutely clear, my dear warriors? This is how you can find the equivalent current due to a rotating charge. Equivalent current due to a rotating charge. So this was also a very important formula which can be useful for these kind of questions, and in general, which the questions involve absolute charges, then obviously you can use current is the total charge flown per unit time. Now, there also comes a concept where you might need instantaneous versus average current, and it makes sense because sometimes the current might keep varying, it might increase, decrease. So every instant the current is changing, and you might want to know, okay, on an average, how much current is it consuming? So if I want instantaneous current, obviously it will be dq by dt. It will be dq by dt. An example for that, let's say, the charge which is flowing in a circuit is 5t cube minus 2t plus 3, okay, coulomb. Can you find what is the current at t is equal to 2 seconds? That is the question. So let's solve it. Current is nothing but dq by dt. So it will be derivative of this q term, which is 5t cube minus 2t plus 3. Okay. Derivative of t cube, 5 is a constant, so comes outside. It will be 3t square. Use x raised to n formula. Nx raised to n minus 1 is the answer. So that's why you will see 3 and power of time reduced. And this will be 2 multiplied by t raised to 1, means 1 into t raised to 0, which is just 1. Constant's derivative is 0. Okay, so this will be nothing but 15 t square minus 2. That is in general the current. So therefore, the current at time is equal to 2 seconds. Just substitute the value of time as 2 and minus 2 over here. Therefore, you will see I2 will be, what is it? 2 square is 4. 15 into 4 is nothing but 60. 15 4s are 60 minus 2. That means it will be 58 amperes. So that's how you can find instantaneous current by looking at the derivative or basically the slope. So dq by dt is nothing but the slope of the charge versus time graph. The slope of the charge versus time graph. So this gives me instantaneous value. This will give me instantaneous value. But when you want to find the average value of current, the average value of current, whenever you want to find the average value of current, when you want to find the average value of current, it is nothing but the total charge. It is nothing but the total charge which has flown, the total charge which has flown upon the total time, upon the total time. Like for example, in the same question, if it was asked, find the average current till 2 seconds. Find the average current till 2 seconds, not at 2 seconds, till 2 seconds. Then how will the solution change? Observe carefully. First, let me find what is the charge at 0 seconds. The charge at 0 seconds, just substitute it over here. It will be 5 multiplied by 0 cube minus 2 multiplied by 0 plus 3. So which is as good as saying it is nothing but 3 coulombs. That is the charge at 0 seconds. Similarly, what will be the charge at 2 seconds? That will be nothing but 5 into 2 cube minus 2 into 2, 2 into 2 plus 3. Okay, 2 cube is nothing but 8, 8 5s are 40 minus 2 2s are 4 plus 3, which will give me 40 minus 4 is 36, 36 plus 3 is nothing but 39. So therefore, the average current will be the charge which has flown. At 0 it was 3 coulombs, at 2 seconds it was 39. So the charge which has flown is 39 minus 3 upon the time interval. Time interval is 2 seconds. So strictly speaking, the total charge flown upon total time, I can also write it as nothing but delta Q divided by delta T. Delta Q divided by delta T. That is what my average will be. So now this is solvable, of course. 39 minus 3 is nothing but 36 divided by 2, which is nothing but 18 amperes. So the average current till 2 seconds was 18, but at 2 seconds it was 58 amperes. Got it, everyone? Yeah. So Vignesh, see, you would have made a mistake. If you would have just done 39 by 2, that will be wrong, because there will be a change in the charge. At 0, already 3 coulombs of charge has flown. At 2 seconds, 39 coulombs has flown. So from 0 to 2 seconds, 39 minus 3, which is 36 coulombs in that interval has flown. So that is one common mistake. That's why I made you guys do this question. Many students usually divide this divided by time. They forget to subtract that initial charge also. Got it? Yeah. Awesome. Hi sir, free DNN. Welcome Sunil. Yes, good evening. Is there any relation between electric field and current? Yes, we are going to come to that. Definitely. Okay. All right. All right. All right. Next, sir, can we find charge by current? 100%. Because if I know derivative of charge is current, integration of current will be charge. So that is also possible. That will also be the area under the curve. So the slope gives me instantaneous current. The area under the current versus time will give me the net charge flown. So I can also write this particular formula. The total charge flown, is nothing but integration of current with respect to time from whatever time interval t1 to time interval t2. This is also a very important thing. So area under the current versus time graph, gives me the total charge which has flown in that segment of time. Integration. We can do a question on that. I think we might have it somewhere over here. Yeah, like so. The variation of current through the cross section of the wire over a period of 12 seconds is shown. How the current is changing with time. Can we figure out the charge which has flown in 12 seconds? 100%. So as we can see over here, the charge which has flown will be nothing but the area under the current versus time graph. Here it is area of the trapezium, area of the trapezium. And the formula for the area of a trapezium, a lot of people will divide it into triangle and rectangle. Don't do that. It's a waste of time. Directly use the formula. It is half into height multiplied by the sum of parallel sides. Half into the height of the trapezium. As you can see over here, this is basically the height of the trapezium, and the height of the trapezium is 6 units. So 6 will come over here, and the sum of parallel sides, this is one side, this will be obviously 6 units, and this is another parallel side, which is obviously 12 units. So sum of parallel means 6 plus 12. So this will be 6 by 2 is 3, 12 plus 6 is nothing but 18 over here, and we just have 18 into 3, which is nothing but 54, which is nothing but 54. So the answer is option A, 54 coulombs. Very straightforward. Yeah. How many of you got it? Very good, Prakash. Awesome. Moving on to the next question on your screen. Here it is. A J Mains 2025 question, this year's question. Current passing through a wire as a function of time is given by 0.02 t plus 0.01 amperes. The charge that will flow between time 1 to 2 seconds is how much? Yeah, how much is it? Is capacitor completed, and why 2 lectures for capacitor? Lakshmi, the main concept of capacitors is done, but the combination of capacitors concepts that with resistors with capacitor, that can be only taught after current electricity. That's why that particular part I mentioned it in the lecture also. That will be doing it, along with combination of resistors, Wheatstone's arrangements, or RC combinations, along with current electricity. There is no separate lecture required for that. Okay. Oh, so let's see the next one. Okay, what is this? The current which is passing through a wire is given by this function. What is the charge which is flowing? Okay, so let's do this, guys. So the charge that will flow will be integration of current with respect to time from T1 to T2. Okay, so what is the current? It is nothing but 0.02 T plus 0.01. This whole thing is the current dt from 1 to 2. Okay, so 0.02 is a number, take it outside. T's integration is nothing but t square by 2, but I have to substitute 2 and 1, upper and lower limits, plus 0.01 is a constant, comes outside. Integration of dt is just time, and the limits will be 2 and 1, of course. Okay, so this 2 and this 2 will get cancelled. It will become 0.01. Yeah, this 2 and this 2 get cancelled, and I'm left with first put 2, so 2 square, then put 1, so minus 1 square, plus 0.01, of course. First put 2 instead of time, and then put 1, and then of course subtract them. So what will be the charge flown be equal to? This will be nothing but 0.01 multiplied by, this is 4 minus 1, which is nothing but 3, plus this is nothing but 2 minus 1 is 1, so plus 0.01 multiplied by 1. Okay, so 0.01, this will become 0.03, so this will become 0.04 coulomb. So that should be the answer, 0.04 coulomb, which is option D. Is that right, everyone? Yeah, very good, Vignesh, very good. Oh, Prakash, no, it's not 0.07. Why did we integrate it, sir? Anamika, see this over here. If current is derivative of charge, charge will be integration of current. So that is why charge will be integration of current or area under that. So you would have seen this in kinematics also. Velocity is the derivative of displacement. Velocity is the derivative of displacement. So displacement is integration of velocity with time. Velocity was the slope of displacement time. Displacement will be area of velocity time. So same thing is applicable throughout maths and physics and chemistry. If some quantity is the derivative of something, then that quantity will also be the integration of the reverse thing. Okay, exact antiderivative is also another word for integration. Now do you remember it? Yeah, I hope this is absolutely clear. Yep. Concentrate on the class, my dear warriors. Yep. So current is a derivative of charge. Charge will be the integration of current. You can just take dt over here. So dq will be I dt. So total charge will be integration of I dt. Integration of I dt. Yeah, correct. So that is why we have integrated current with time with the proper limits. Limits we can get it from the problem itself. That has to be given, obviously. Without that, we cannot do it. Okay, so that's why the answer was 0.04 coulombs. Okay, now comes the next concept of current's density. How dense is that current? How dense is basically the current? So say for example, over here, I give you a scenario like this. And let's say this is the cross section of some wire, okay? And let's say through that cross section, we have uh, some three charges coming out versus that same three charges coming out through a bigger cross section versus through that same cross section, more number of charges are flowing through that cross section. Here, as you can see, area is the same, but here the area is more. So maybe this is A prime, which is more than A. Here, as you can see, the current, whatever is flowing, is the same as the current flowing here. But here, let's say the current is I prime, that is more than this current. This is exactly the concept of current density. If I tell you how much current is flowing per unit cross section, that is the concept of current density. So current density, well, current density, current density, current density. The symbol of current density is basically J, is nothing but how much current flows, which is basically I, divided by the area of cross section, As you can see, current is measured in amperes. And area, of course, is measured in square. So that is exactly the unit of current density. The unit of current density. The unit of current density is ampere per meter square. Now over here, can you now compare the current densities? If the current density is J over here, because the area is big, obviously the denominator will be more. Current density, it is not as dense as over here. Here the lines are spaced closely. Here it is less dense. So J is less due to larger area. If the area was small, the current density would have been higher. Here current density is more. Here J is more due to large current, due to the larger value of current, Is that absolutely clear, everyone? So current density can vary because of either the current changing or because of the cross section of the area changing. One of them, right? Correct. Very good. Now understand this. Okay. Perfect. Everybody understood? Yes, Anamika understood this. Yes, Prakash, J is I by A. Correcto. Awesome. Now, this current density, please remember, it is a vector quantity. It is a vector quantity in the direction, of the flow of positivity, that is basically the current. It is a vector quantity which is in the direction of the flow of positivity, basically the same as the direction of current. Here current is flowing this way. So J vector current density is also in the same direction. Here also it is in the same direction. Here also it is in the same direction. Now this becomes particularly useful in these kind of questions where, imagine, this is a very interesting thing. Observe this now. This is very, very crucial, guys. Now, let's say, for example, there is some amount of current coming in over here, some amount of current coming in over here, and some amount of current leaving through this cross section. You guys quickly think and tell me, this is some parts of the wire. This is a perfect, vertical part. This is a oblique or a slanting part of a wire. Okay, just imaginary cross sections. These are not real cuts. These are imaginary cuts. Okay, this is a long current carrying wire. Okay, just imagine this is a long current carrying wire. These are all imaginary cuts which have been made over here. Now think and tell me, where do you think the current will be more? Answer it in the chat box. The left cross section which is flat, or the slanting one, this number 2, or the right side one. Tell me one thing. If 10 charges enter inside, how many charges should leave from the slanting cross section? If you tell, no sir, it will be less than 10. My question is, let's say if 10 charges come in and you are saying 8 charges are coming out, where did the 2 charges disappear? It can't disappear. Okay, sir. Sir, 10 charges went in, 12 charges came out. Where did extra 2 charges come from? It can't happen. So whatever number of charges enter in, same number of charges should exit out. Isn't it? So the current should be the same. Yes, the current should be the same, my dear warriors. Got it? Yeah. So very, very important. Whatever current is there on this side, so number of charges going in per unit time is equal to the number of charges which are coming out per unit time. So the current which is going in is the current which is going out. I can just say it is I. So this is just, I'm assuming it. Let's assume the current to be I. That is very, very important. And where is the current density, my dear warriors? The current density is always in the direction of the current. So the current density will be like this, needless to say. And same thing over here, the current density should be like this. Okay, the current density, oops, my God. The current density should be basically in the same direction. So this is basically J. This is also basically J. Now, will the current density be equal? Will the current density be equal? That is the next kind of question that you should think about. Okay, let's call this as J1. Let's call this as J2. I don't know whether they are equal or not. Let's just take it. If you ask me what is J1, well, J1 is nothing but current by area. So the current over here is that same current I divided by that particular area, of cross section which you are seeing over here, this particular area, isn't it? So this particular area, how much is it? Well, it is nothing but A. So J1 is nothing but I by A. But here, if you ask me what is that area, well, area is also a vector quantity. Here, if you ask me what is the area vector will be like this. Here, area vector will be like this. But here, that area vector will be making some angle. Here, that area vector will be making definitely some angle. And if you ask me how much is this particular area, what will your answer be? Logic goes like this. Think about it. This flat area, vertical area, was A. How much will this slanting area be? Just think about it carefully, my dear warriors. Just think about it carefully. So if this is A, this is perpendicular, you tilt it by an angle theta. Well, the hypotenuse and this adjacent side, cos theta is nothing but adjacent side by your hypotenuse. So therefore, the hypotenuse will be A by cos theta. It will be nothing but A by cos of theta. Everybody agrees to this? Everybody agrees to this. It will be A divided by cos theta, not A cos theta. This particular area will be A by cos theta. We are talking about the hypotenuse itself. If this was A, this will be A cos theta. If this was A, this will be A cos theta. So think about it. This technically will be nothing but A divided by cos theta. A divided by cos theta. So if somebody asks me what is J2, what is J2, I will say it is nothing but that same current divided by A by cos theta, divided by A by cos theta. Is that right? Everyone with me on this? Perfecto. But usually what happens is, if I want to find the current density here, then I will consider this area only A, and then whatever other areas are there, I will accordingly, manipulate it. So if I assume this area itself as A, this area itself as A, that means my hypotenuse is A. If my hypotenuse is itself A, then this side, how much should it be? Just think about it. Cos theta will be nothing but my adjacent side divided by hypotenuse, which is A. Therefore, the adjacent side will be A cos theta. So this will be A cos of theta. Everybody gets it? If this is actually A, this will be A cos theta. So if this area is A, this will be A cos theta. Keep this in mind. So this I can put it A cos theta then, and this will be nothing but just A. Everyone till this point? Everyone till this point absolutely clear? Everyone till this point absolutely clear? Yeah. But now here is the thing. Whenever you want to write in terms of vectors, and I know current density is a vector, area is a vector, right? Area is a vector, current density is a vector, okay? But current is a scalar quantity. This is vector, current is a scalar quantity. So we write it in terms of the dot product, something like this. Current, I can just write it as the current is nothing but the current density vector dot producted with the area vector. So no matter how I choose my area, always the dot product of area with current density, which will give me the current, that should somehow come out to be the same. So if I measure the current over here, it will be J2 into A. If I measure the current over here, it will be J1 into A cos theta. So if you want, you can take this as A cos, this as A, or you can take this as A by cos, and you can manipulate it however you want it. That is not the point. The point is, if you take it as a dot product, everything becomes simple. Okay, so this could be my area vector. My current might be going in this particular direction, which is also the direction of my current density. And if there is an angle which is made, which I call it as theta, so therefore my current will be nothing but J into A into cos theta. J into A into cos theta. That's what you should keep in mind. Whenever you write current, make sure you put dot product between current density and area vector, because they might not be in the same direction. Is this clear, my dear warriors? Yes, Rama, for the previous question, this area is definitely going to be more. So you can compare the current densities directly from here. The current densities will definitely not be equal. Can you see that current densities are not equal? So to answer the question, is J going to be the same? The answer is 100% no. You can see it right only from here. Cos theta will be lesser than 1, like 0.8, 0.7, 0.6. So when you divide by a smaller number than 1, the value will increase. So current density will be more over here as compared to this. So this is definitely not equal to, this one is more, this one is less. And it kind of makes sense, because if you take a slanting area, I have that huge area, but the current flowing through that is the same. So how will the density be the same? So through a large area, same current flows. So that is why the density is less over here. The density is definitely lesser over here. Okay. So this is how we define current density in terms of current and area. Should remember this. Okay. It's a dot product. Okay. So dot, or basically scalar product. Dot or scalar product. Yesterday only in the 11th standard class we have done this. So anyways, going to some question. I think we might have a question on this. Okay, wow, what a question. The current density in a cylindrical wire of radius 4 millimeters is this much. The current through the outer portion of the wire between the radial distance r by 2 and r is something pi ampere, where x is how much? Okay, interesting. Let's understand what this question actually means. So let's take a cross section like this. Let's take a current cylindrical wires cross section. This radius is r. Let's take that particular radius as r, and that r is given to be 4 millimeters. 4 millimeters, which is the same as saying 4 into 10 to the power minus 3 meter. That's it, meters. Current density is given. The question is, what is current through the outer portion of the wire between the radial distance r by 2 and r? So where is r by 2 going to be? Well, r by 2 will be somewhere over here. R by 2 will be somewhere over here. Okay, this is, let's say, our r by 2, which is nothing but 2 millimeters. It is the same as saying 2 into 10 to the power minus 3 meters. So if you take the radial distance between r by 2 and r, what is that area that we are talking about exactly? We're talking about this much portion. Just check this out. If this is clear, we're talking about this much portion. How much current is flowing through this much portion is being asked. Are you able to visualize this now? How much current is flowing only through that annular portion, this much portion of that particular cylindrical wire. Guess what is same throughout that cross section? Can you guess what is same throughout that cross section? Well, if you have not been able to guess it, let me tell you. Very easy it is. It's basically how much current is flowing per unit area, which is nothing but the current density. The density of the current is the same throughout that cross section. It will not change because the material is the same, no non-uniformity or anything like that. So it is current density which is going to be the same. So current density is the same. Current density is the same throughout that cross section. So if you take the total area, then the total current through that will be something. So let's say, the current density is given already. So let's say I take the total current upon the total area, which is basically pi r square. That will give me the current density. Also, I can say that the current density is same only in this much part, that between that 0 to r by 2, current is the same. Also, current density will be current flowing in that inner part by that inner area, which is basically pi r by 2 whole square. Yep, I can still say that. And the question is, how much the current flowing through the outer portion of the wire is asked. So if I subtract the total current through the total wire, minus the current flowing through that inner part. Whatever is remaining will give me the current flowing in that blue shaded region. So here I can clearly see that I total, that the total current will be nothing but J into pi R square. And over here, I can see in that inner part, the current will be J into pi R square by 4. So if I subtract these two, the total current flowing from 0 to R minus only the current flowing from 0 to R by 2, whatever is remaining is the current flowing in this blue part. So to find that, so the current flowing through the outer portion of the wire, if this is what we want, it will be nothing but I total minus I flowing through the inner part. I total is nothing but J pi R square. I flowing through inner is J pi R square by 4. So 1 minus 1 by 4 is 3 by 4. So 3 by 4 J pi R square. That's it. So 3 by 4 is as it is. J value is given to be 10 to the power 6 SI units multiplied by pi, and R square. R is 4 into 10 to the power minus 3, but whole square it. Okay, so a lot of things will get cancelled. This minus 3 square will become minus 6. This 4 is also going to get cancelled later on, but okay, let me just put it as it is. 10 to the power 6 multiplied by pi. This is 4 into 4 multiplied by 10 to the power minus 6. So see what and all get cancelled. This 4 and this 4. This minus 6 and plus 6. 4 threes are basically 12. So hence you will get 12 pi amperes. 12 pi amperes. So that is the answer. X is basically 12. Answer is 12. Got it? This is a beautiful question to explain you current density concept. Yeah, absolutely clear. Everyone? Awesome, awesome, my dear warriors. Perfecto. Great. Shall we go ahead, guys, to the next concept, next question? Yeah. So current density was involved over here because current per unit area will be the same for that entire 0 to R. The current was I total. From here to here, only in the green part, this was that current. So if you subtract these two currents, what I will get is from this, I subtract this, how much current is flowing in this much part. That is what I will get. Yeah. So that is what this is, Prakash. So think of it one more time. When you take the total current, it was the current which was flowing through the entire cross section minus the current flowing from 0 to R by 2. That will give me how much current was flowing only in this much part. How much current was flowing in this much part. That is what we have done. Okay. So total current was J into A, but areas were different. So you subtract the two, you will get the current through that annular region. That is what we have done. See if it is now clear, Prakash. Yeah, this question mainly mathematics, correct. Sometimes the questions can be just on, what do you say? Even dot products, like some weird simple question, like let's say there is a cross section, of let's say, you know, uh, 3 meter square in YZ plane, and let's say they give you there is a current density, of 4 I cap plus 2 J cap ampere per meter square. Question will be how much current is flowing through it. As you can see over here, that area is 3 meter square in the YZ plane. That means if you think of the YZ plane, Y is this axis, Z is this axis, and X is basically this axis. So that particular area is like this. So the area vector will be maybe in this direction. So that area vector will be magnitude, which is 3, and direction is I cap meter square. So that is what that area will be. There is some current density which is given, some 4 I cap plus 2 j cap. So that means it will be like this. So this is your current density vector. So how much current is flowing through it is asked. So as you can see, we can simply use current is j vector dot area vector. J is 4 I cap plus 2 j cap dot area vector, which is 3 I cap. So I will multiply only with I. So 4 into 3. There is nothing for J. So 0. So it will be nothing but 12 ampere. So the current will be 12 amperes. Cool? Yeah. So these kind of dot product based questions can also come in your J examination. Cool, sir. We got it. Now let's go to the next concept of how these fields and drift speeds and mobility and all these things are now going to come into play. Okay. See, when you take a conductor, the electrons are moving rapidly, randomly in all the directions. So when there is no battery connected, so in an isolated conductor basically, so in an isolated conductor without any potential difference, that is when there is no battery connected, the electrons move randomly. The electrons move randomly. So the average velocity is 0. The average velocity is 0. The net charge flow is 0. Also the current in that conductor is 0. If 5 charges go this way, some other 5 charges will come here. If 7 charges go up, some other 7 charges will come down. You take any direction, you will see almost on an average no net movement will happen. Some or the other charges will cancel it out. So there is no net movement. But keep in mind the electrons, but the electrons do have speeds due to the thermal energy, because of temperature. You will study that in kinetic theory of gases or have already studied that in KTG whenever you have molecules or anything, atoms, molecules, whatever. So because of the temperature, they have thermal energy, they keep on moving rapidly, and these electrons are also having thermal energy, so they keep on colliding with each other, they keep on changing their directions, random motion is there, but no net motion can be observed. On an average, everything just averages out to be 0. That's what is happening. Now, this is the situation when there is no battery connected. What will happen? What will happen the moment you connect a battery? Suddenly, you will start seeing the electrons are getting biased, they are getting partial. They will start moving because of the voltage difference, and in such a way that the electric force is pushing them in one direction. So, the moment the battery is connected, basically there is a potential difference. There is potential difference in the conductor. There is definitely potential difference in the conductor. So what will happen? There will be an electric field. So let's say, for example, this over here, positive terminal, this is, let's say, high potential. Let's say this is basically your high potential. This side negative terminal, so low potential. Whenever there is a potential difference, what will come into play? Electric field. Do not forget that. Yeah, so there will be electric field from high voltage to low voltage. So there will be an electric field, and this electric field is there inside the conductor, which is due to the voltage difference or the battery. So if you talk about negative charges, the force on it will be exactly in the opposite direction. So this is the direction in which the force will act. So there will be a force on it. So there will be an electric force on it. That is why you are seeing the electrons are moving towards this side, but negativity is going there. So that is the reason why the current will go in the opposite direction. So the current will be in the direction of the electric field only. So the electric current will be in the same direction as the electric field, but the electric force and the motion of the charges will be on the other side. They are negative charges, so don't worry about it. So even the motion of the charges, even the velocity of the charges, even the motion of the charges is exactly opposite to the field or to the electric current, because they are negative. If they were positive, all the directions would be same. Is this diagram clear? Put up a fire emoji, and if you have forgotten to smash the like button, please do it right away, right now. Yeah. Yes. Ask the doubt. Sir, the electrons completely changed or only their charge? I didn't get you, Rama. Why will electrons change? Yeah. So the electrons are now going in one peculiar direction. Now you will see that the motion of the electrons, which was on an average 0. Okay, so let me make a duplicate. So on an average, let's say the electron was going like this, colliding somewhere, then again going like this, maybe again going like this, then again going like this, again going like this, maybe again going like this, and then maybe again coming back over here. So in this particular scenario, as you can see, the electron without any battery, when there was no voltage difference, was going like this, and as a whole, it was having zero displacement. As you can see, zero displacement on average. This is without any battery, but with the battery connected, you will definitely see the electrons will begin to move. They will start moving in the direction of the electric force. So you will see, maybe instead of now going here, it will now go here because of the force. Now it might reach here, maybe. Okay, just Shoma giving you some things. So maybe it will go here, maybe it will reach 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 here, and finally maybe it might come over here. So with the force acting on it, the electrons are now slightly getting drifted. As you can see, the electrons are slightly getting drifted in the rightward direction. And after the same number of collisions, instead of reaching here, it is reaching over here. So this particular velocity with which the electrons drift, is called as the drift velocity. So they are drifting slowly and steadily in one peculiar direction, in the direction of higher potential. That is called as the drift velocity. Is that clear? Everyone with me? Everybody with me? Yeah. Now, there are three important speeds that you need to keep in mind. First things first, the electric field. The electric field which moves inside the conductor, it is almost instantaneous. Remember, electromagnetic waves, light, the electric field travels at a very high speed, that is the speed of light. So electric field is set up almost instantly inside the conductor, almost instantly. That is at the speed of light, which is 3 lakh kilometers per second, or 3 into 10 to the power 8 meters per second. That is the speed at which the field will be set up throughout the conductor. So the moment you connect the battery, electric field is there almost everywhere instantly within a fraction of a second. So all the electrons now know, okay, I have to move, I have to move, I have to move, I have to move, I have to move. But when they start moving, they don't move at the speed of light. They will move slowly. So that is drift speed. The drift speed, the drift speed is very small, Typically, in few micrometers to millimeters per second. Typically, this is typical speeds, hardly few millimeters or micrometers per second. So it takes hours or days for the electrons to move from one point to other point. This was a very famous question of reasoning in JEE. If the electron drift speed is so low, how is it that when I turn on the switch, the bulb glows instantly? Won't the electron take few minutes, few hours or days to reach the bulb? Yes, correct. That same electron will not reach that bulb instantly, but it is the electric field which reaches. So an electron over here also moves, here also moves, here also, everywhere it starts moving. Even in the bulb, it starts moving instantly. So that electron which is in the bulb, which has started moving, makes the bulb glow or the device work. It's not this electron has to reach there. Okay. So that electric field is carrying that information. Is this absolutely clear? And lastly, the speed of the electrons themselves. The electrons themselves, the electrons due to thermal collisions, due to thermal collisions have medium speeds, have medium speeds, have medium speeds from few, hundred, hundreds to thousands of meters per second. Okay, so few couple of thousands, 10,000s, 90,000, 50,000, like that. So that is the typical range of the electrons moving inside, tuck, 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 thousands of meters per second. But even though they are moving thousands of meters per second, they are moving, drifting slowly. So tuck, 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 they keep moving, but slowly they will move. After 1 hour, you see this electrons which was here, now they are started to move over here. So they are drifting very slowly, although their individual speeds, actual speeds are more. Okay. Is this absolutely clear, my dear warriors? Everyone with me? This is one concept which many students do not know, and JEE can play with your mind. They can play with your concept just on this theory point. Okay. Keep this in mind. All right, sir. So how much is this drift velocity, sir? How much is this drift velocity? Well, we can find that out. It is not that difficult. So say for example, how much is this drift velocity? So let's say for example, the total length of the conductor is L, the area of the cross section is A, the drift speed is V. So let's say that the electrons, the electrons inside the conductor drift with a speed of Vd and take time t to cross that length L, then I can easily say that drift speed is nothing but the length divided by time. It's moving with speed v. Speed is distance by how much time it takes. Okay. Now, if these electrons enter and exit, think of a bunch of electrons which have now entered over here, or a bunch of electrons which were here have now exited out. So how many charges in the time duration cross that section? Basically, how many charges exit out or how many charges enter in? That is the number of charges crossing any cross section in that conductor. So to find that out, we can do like this. The number of charges, which are crossing per unit time is nothing but the total number of charges, upon the total time taken. How much is the total number of charges? I have an idea. What if I tell you there is a quantity called as n, which is specific of that material, which tells me the number of charges, which are there per unit volume. This completely depends, I tell you, this depends on the material, and that is usually given to you. For aluminum, so many charges are there per unit volume, per meter cube. For copper, more number of charges are there. How much ever it is, that much volume, in one volume, unit volume, how much is there is given to you. So charge carrier density, the number of charges per unit volume, which depends on the material, small n is given to you. So the total number of charges, will be nothing but that particular n multiplied by the volume, and the time taken, we can get it from here. So you can clearly see that the time taken will be L divided by VD. Time will be L divided by VD. So I'll take L over here and divide it with drift speed. So next step, my drift speed will go on the top, length will be here only, and of course N will stay as it is. And what is the volume? Volume is nothing but area multiplied by length. As we can clearly see that the length term has got cancelled. So this is the number of charges crossing per unit time. This is the number of charges crossing per unit time. This I have seen it somewhere. I remember seeing it. If you observed carefully, here, where is it? Yeah. Current is N by T into E. Current is number of charges which are crossing per unit time into E. Oh, that's great. So what can we do over here? Yes. So we can just say, therefore, 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 current being N by T into E, therefore current being N by T multiplied by E, just substitute the value, which is drift speed, into basically our N which is there, multiplied by that area, and of course that E from the previous equation. That is basically the current. So rearranging it, yeah, so from this we can easily say current is nothing but NVDEA, a very, very important formula. Current is NVIDIA. Current is NVIDIA. This is a very famous company now, NVIDIA. Yeah, world's #1 company, NVIDIA. So current is NVIDIA. Okay, D is the subscript, it is not multiplied with velocity. So keep that in mind. Okay, just 1 second, guys. Okay, cool. Now I can play around with this formula. I can play around with this formula a little bit more, and I can show you something more. Relation between current and drift velocity we have done. Okay, 1 second. Not needed. So since current is NVDA, how about taking area below? So current by area is NVDA. Yeah, but A is below. But what is current by area? It is nothing but current density. Current density is NVDE. Current density is NVDE. That's it. So this is a new formula. But current density being a vector and drift velocity also being a vector, let's go back and see what is the exact manner in which I can put a vector symbol. See, current is going this way, so current density is this way. Drift velocity is the other way around. Can you see drift velocity is other way round? So it's exactly opposite of the drift velocity. J is exactly opposite of drift velocity. Can you see that? J is exactly opposite of the drift velocity. So if I put, this is nothing but scalar representation. This is nothing but scalar representation. If I put it in vector form, J bar will be NVD bar E, but there should be a minus sign considering the fact that drift velocity and current density are exactly opposite. We just saw it over here. Where is that? This particular diagram. Drift velocity is that way, right side. So drift velocity was like this, but the current was going this way. So that is why the current density vector will be this way. Current density vector will be this way. They are exactly opposite of each other. Now, some books, what they do, they consider E to be positive. Some books, they say E is the charge. So if I take the charge itself as negative, then I don't have to put that minus sign. So then some books, then what they do is they don't write that minus sign and they assume that the value of E is negative 1.6 into 10 to the power minus 19 coulomb. So if the negative sign is included in the charge, then no need to put the minus sign. But if it is excluded in that charge, then put that negative sign. Is this very clear? When to consider negative or when not to consider negative? Yeah, got it, Rama, everyone, Akshu, Sai, perfect, excellent, understood. Yeah, so this is nothing but the vector way of representing it. But here I have assumed that E is negative 1.6 10 to the power minus 19 coulomb. Otherwise, you can, if you take E as positive, then you, or mod value, then you put negative sign over here. Yeah, clear, Mohammed? Awesome. Sumit, everyone, great. Okay. Now, when we were showing this particular diagram, where the electrons were colliding, moving randomly. Same thing here also. It was colliding randomly and slowly drifting. So between one collision to the next collision, there was some time where the electron was like, habba, nothing I have to worry about. So it was relaxing for some time. So imagine when these electrons are drifting forward, okay, and they move some distance. Between one collision to the next collision, there is a time for which they are just relaxing, they are moving in a straight line. So that time for which the electrons relax without any collision is called as relaxation time, as the name suggests. So if our electrons are going like this and our electric field is like this, and our force on the electron is going to be this particular way. The drift velocity is like this. So the time between successive collisions is called a relaxation time. The symbol for that is tau, like the torque symbol. You don't use small t or capital T. Tau is usually the symbol for relaxation time. We can get that formula very easily. It's not that difficult, using kinematic equations only. So using kinematic equations, final velocity is equal to initial velocity plus acceleration multiplied by the time. Final velocity is my drift speed. After the collision, the speed becomes 0, okay, plus acceleration. Well, from here we can easily see that acceleration is force by mass, but force on a charge is the charge multiplied by the field. So acceleration is E by m. So acceleration is E divided by m, and this time is nothing but our relaxation time. So from this we can also write down our drift speed is nothing but E by m multiplied by tau. E by m multiplied by tau. So you can find the relaxation time also using this particular equation. We can find drift speed from here. We can find drift speed from, where is that? This equation. Drift speed from this equation. From drift speed, we can also find current density also, or from this, we can also find the relaxation time. All things are possible. So let me give you a simple example. Say that the number of charge carriers per unit volume is 10 to the power 20 per meter cube. Let's say the current is of 10 ampere. Let's say the area is 0.1 meter square. Okay, and the question is, or let's say the current is 16 ampere. Chumma, can you find what is the drift speed? Also find out what is this thing, the relaxation time. Also find what is the relaxation time. The mass of an electron is 9 into 10 to the power minus 31 kg. Okay, all these things are given to. So let's see how do we solve this. Let's start by finding out the drift speed first. Since I know current is NVDR, so therefore drift speed will be current divided by NE and A. NE and A over here. Current is 16 amperes. Number of charge carriers is 10 to the power 20. Electron charge is 1.6 10 to the power minus 19, and area is nothing but 0.1. Okay, perfect. So this I can do one thing. This 20 and minus 19, 110 will remain. 10 into 1.6 will be 16. 10 into 1.6 will be 16, and divided by 0.1. 16 cancels, so this will become 10 meters per second. So that is a drift speed which is very large. Usually it doesn't happen, but for this particular question it has happened. Don't worry about the values, but I'm just showing you how to calculate it. Okay sir, drift speed done. How do I find relaxation time? Let's see. We all know drift speed is nothing but E by m into tau. Oh sir, electric field is not given, so I think some other data will be given. Let's say the potential difference which has been applied is 10 volts. Potential difference which has been applied, okay, is 10 volts, or let's say it is 18 volts or something. And the length of the conductor is, let's say, 10 meters. Length of the conductor is given to be 10 meters. From this data, if the battery's voltage and the length of the conductor is given, my job is done. Potential difference and length gives me electric field. Yes, electric field can be easily calculated. How much will be the value of electric field? Electric field is potential difference per unit distance. Potential difference is 18. Distance is basically 10. So it is nothing but 1.8 volts per meter. I can use that over here now to solve it. So that data always has to be given, or else we cannot solve it, of course. Drift speed, we got it to be 10. Okay. Electron charge is 1.6 10 to the power minus 19 multiplied by the field, which is nothing but 1.8, of course, multiplied by the relaxation time, which I do not know yet. Mass is 9 into 10 to the power minus 31 kg. Okay. So as you can see over here, a lot of things will have to be cancelled and all of that. So 10 will be equal to, first of all, this is 1.8. I can write it as 18 into 10 to the power minus 1. So I can also write it as 1.6 into 10 to the power minus 20 multiplied by 18 divided by 9 into 10 to the power minus 31. Now when I do that, things start looking good. This will be 2 times, and this is minus 20, this is minus 31. So this will become minus 11, of course, and relaxation time is over here. Okay, so 10 multiplied by, this is 10 to the power minus 11. Whole thing divided by 2 is there over here, and this 1.6 is there, is nothing but my relaxation time. Can you see that, guys? So relaxation time is that 2 came down, even that 1.6 came down, 10 to the power minus 11 went up. So this multiplied by 10 will become 10 to the power minus 10. So it will become 10 to the power minus 10, and divided by 1.6 into 2, which is 3.2. So that much is the relaxation time. Yeah. Is this absolutely clear, my dear warriors? These many seconds. Everyone with me? Clear? Yes or no? Perfect. Give me a thumbs up, guys. Everyone. Everyone. Yes. Everybody. Very good. Very good. Very good. Very good. Very good. So that was your relaxation time. You can put it in seconds, you can convert it in decimals also. 1 by 3.2, you can just do that. So 1 by 3.2 into 10 to the power minus 10 seconds. That's the answer. So that's how you use this formulas for drift speed and everything else. Okay. Now we have one more term to define, and that is called as mobility. See, all these terms initially you might struggle, but with some practice you will be like, "Ha, sir, I know the derivation. Now I know how it works. What it means." Okay. So mobility means how mobile the carriers are, how easy it is for the charge carriers to. It's basically the ease of travel of the charge carriers. Mobility, the symbol is mu. So mu is nothing but mobility. Mobility is nothing but how much is the ease of travel, that is measured by drift speed per unit electric field. So mobility is nothing but drift velocity per unit electric field. Dimensions, units, etc. You can find it out easily. It is not very difficult. So unit of mobility you can easily find out. Drift speed is meter per second. Field is volt per meter. So meter goes on the top. So meter square per volt second. That is the unit. So meter square, second comes with volt. So meter square per volt second is the unit of mobility. So how much is the drift speed per unit electric field? So going back to the previous question, which was over here, if the mobility was asked, let's say mobility was asked, mu was asked, mu, as we know, is drift speed per unit electric field. So mobility will be drift speed, where is it? It was 10 per unit electric field. Electric field was 1.8. So that's it. That is mobility, guys. So mu is 10 by 1.8 or 100 by 18, you can say, meter square per volt second. You can reduce it to the smallest fraction. Yeah, we can call it 50 by 9 also. Yeah, we can call it 50 by 9 also. So this is nothing but 50 by 9 meter square per volt second. That is the mobility. In case it was asked, but it is not asked here, is Chuma doing the question for you. Okay, so this was that question which we just did just some time back. Cool? Understood? Mobility, drift speed, everything. Till this point, absolutely clear. Formula for relaxation time, I just gave it to you over here. Vd is EE by M into tau. This is the formula for relaxation time. If you know drift speed, you can find relaxation time. Sir, how do I find drift speed? If you know current or current density, through this you can find the drift speed. Okay? Yeah. Wheatstone bridge, not now. Later on. Yeah. Not now. Galvanometer meter bridge is in the next class or something like that. Okay. So let's see, guys. Questions coming up on your screen, and here it is. The previous year question. The drift speed for a conductor connected in an electrical circuit is Vd. The conductor is now replaced by another conductor with the same material and the same length, but double the area of the cross section. Then the applied voltage remains the same. The new drift velocity will be how much? So earlier you had this. Now double the area of cross section. So earlier this was area A. Now this is basically 2A. The voltage is the same. The voltage is obviously the same. Length of the conductor, I think same material and the same length. Yes, the length of the conductor here and here is the same. Question is, figure out the drift speed. How much difference will be there? Now, logically speaking, if you use the formula, current is equal to NVDA. This N depends on the material, and because the material did not change, 100% it should be the same. E is a constant. This E is a constant, so that will anyways not change. Area has become 2 times. So what will happen to drift speed? Lot of people say, sir, area became 2 times, so the drift speed should become half to make the current the same. That was the trick in this question. A lot of students felt that because area became double, to keep the product same, what do you easily say? It should become half times. But this is wrong, guys. This is not correct. Why is it not correct? Because how do you know that the current will remain the same? Oh, sir, why not, sir? Voltage is the same, length is the same. How do you know the resistance hasn't changed? How do you know the resistance hasn't changed? So current may or may not remain same. So we'll have to revisit this question after looking at resistance. So that was the catch I wanted to show you. We'll come back to this question. But do you understand why current may not be the same? How many of you understood that catch? Because resistance of these wires may not be the same. So even though the voltage is same, resistance changes, current will change. Yeah. Okay. So we'll do this later on. We'll come back. But sir, something similar on the cross sections. Do you have a question? Of course, why not? Imagine there is a wire like this and it becomes big like this. If you compare current here versus here, where will the current be more or where will the current be less? This is cross section 1. This is cross section number 2. Well, if you ask me I1 versus I2, the same charges will go here and here. So currents will be the same because charges are conserved. Charges are conserved, obviously. So it should be the same. But if you ask me current density, which is current per unit area, then J1 versus J2, think about it. This will be I1 by A1. This will be I2 by A2. This area is more, this area is less. So this J1 will be more than this J2. This area being more, this ratio is small, so J2 is less. Less density here, more density on this side. Is that right? Very good. What about drift speed, sir? Okay, for drift speed, let's think which formula will I need? Drift speed at 1 versus drift speed at 2. Current is equal to NVDR. Current is the same, N is the same, E is the same. So whichever has more area will have less speed because current is anyways the same on both the sections. So more area, less speed. More area, less speed. So more area is less speed. So VD2 is less than VD1. Okay, perfect. Till this point also everything clear? Everyone? Very good. Now, what about mobility? Oh, mobility, sir. Drift speed per unit electric field, but I don't know where is the electric field more or less. So how do I know whether electric field is more or less? Maybe I need something else. So we are missing out on something. As you can see over here, if the question was on electric field at 1 versus electric field at 2, or the question was on mobility in this place versus mobility in this place, I'm lacking some information for electric field and mobility. So same problem here and also the same problem here, lacking some information, and that has got to do with resistance. So let's figure out the resistance now. Okay, let's figure out the resistance. But before that, let's see one more question. Which of the following graph represents mobility with field in a conductor? Mobility with field. Come on, guys. Very simple. Yeah, come on, everyone. Think carefully. Yeah, what do you think is the correct answer? Yes, correct answer is obviously C. Mobility is independent of the electric field. Mobility is that property of that material. Okay, so if you take aluminum, iron, copper, silver, gold, how mobile they are depends on that material. So yes, it feels a lot of times that mobility being drift speed per unit electric field. Lot of people think mobility is inversely proportional to the field, but that is wrong. In fact, mobility depends on the material. If field changes, drift speed changes, mobility will not change. So if somebody increases the field, the drift speed will increase, but this is not going to change. It is going to be the same for the material, for a material at a given temperature. This is going to be the same. Yeah, a lot of students make that mistake. Okay, so they say it is inversely proportional. Sometimes people misplace the formula, they write E on the top, so they feel it is directly proportional, more field, more mobility. No, nothing like that. Okay, so it is the same. A lot of students make that mistake, so I wanted to point this out. This can be your previous year question too. Let's do one more question on your screen. The current of 10 ampere is existing, area is also given, drift speed is also given, the number of free electrons in each cubic meter of the wire. So what they have asked, number of free electrons in each cubic meter means N, number of charge carriers per unit volume. Yeah, that's what they have asked. So which formula do I use? Current is there, N I don't know, Vd is given, I think, E into A. E is also E is standard, area is also given. Perfect. So we just have to find N. So N will be nothing but current divided by drift speed into electron charge into area. Current is how much? It is given to be 10 amperes. Whole thing divided by drift speed. Velocity is 2 into 10 to the power minus 3. Okay. Multiplied by electron charge, which is 1.6 10 to the power minus 19, and area is nothing but 5 millimeter square. So millimeter is 10 to the power minus 3, squaring it will become minus 6 in meter square. So 5 millimeter square is 5 into 10 to the power minus 6 meter square. Keep that in mind. Now you can easily solve this. Yeah. Now you can easily solve this. Solve this and see if you're getting the answer close enough to 625 into 10 to the power 25. Okay. Just see, solve this. You should get the answer. Very straightforward question which was asked in J 2021. Yeah. Very good. Of course, man. We were all together. Thunder. You guys didn't come. Shreyas Anand. Nice to see somebody from my by my name. Very good, Shreyas. Awesome. Feels nice praising me. Please keep answering more and more. Okay. So this question I'm going to give you as a homework. Okay. This question, please solve it as homework because it is very similar. Now this will be the third variety of question again we are solving. So where are you going to put the answers? The answer should be there in the comments. Like in the starting of the class, I will tell who all students have. I'll show the names next time. Okay. I want everybody, please solve the homework question. Solution is there on the next slide, but don't look at the solution. Only when you don't get it, look at the solution. Don't worry even if your answer is wrong. Don't worry. We don't judge anyone. If it is wrong, it is in fact good. You have learned something. You have made a mistake, not in the exam, but at home. That is always better. Okay. Do as many mistakes as possible at home than doing it at the exam. Yeah. Great. So that is your homework question. Now let's go to the resistance part and then we'll come back to those questions, and that brings us to something called as Ohm's law. Ohm's law. So Ohm's law is nothing but whenever you apply a potential difference across the conductor and you change that potential difference, the current passing through it linearly varies as the potential difference. So the current flowing through a conductor is directly proportional to the voltage difference across the conductor. So current versus voltage graph is a straight line. That is what simply Ohm's law is. So if I had to write it down, V is directly proportional to current. The constant of proportionality is called resistance. The constant of proportionality is obviously going to be called as resistance. If there is more resistance, for that same voltage, there will be less current. If there is very little resistance, the current will be more to keep the product constant for the same voltage. Kind of makes sense. Also, for the same current, if there is more resistance, there will be more voltage drop. So voltage will be proportional to the resistance if current is the same. Same current is going, more resistance is there, voltage will drop by a larger amount. Okay, so V is equal to IR. So the unit symbol, everything, symbol of resistance, everybody remembers it used to be like this. Yeah, this is the symbol. Unit, SI unit is nothing but ohm, or using this symbol, that is fine. And the ohm of resistance, you can see voltage is in volts. So when there is a voltage difference of 1 volt for a ampere of current, 1 ohm is 1 volt per ampere. You take current below, volt per ampere is the unit of resistance. That is the symbol also of resistance. But Ohm's law is not all that nice every time, and there is a and in fact there are many exceptions to it. So if I have this is voltage, let's say this is current, usually our graph should be a straight line. When this happens, that is voltage is directly proportional to current, such a device is called as a ohmic device. Ohmic device. So ohmic devices, example, most of the conductors, you will see the relationship is straight, but there are a lot of devices which will show the graph like this, or maybe even like this, or even maybe something like this. Maybe it will go like this. Okay. Any kind of another graph which is not proportional, they are basically non-ohmic devices. So non-ohmic devices, like example, semiconductors, diodes. Even for a capacitor, the voltage is not proportional to the current passing through it. I mean, it's not. So, a lot of devices are there for which it is not proportional. So, the resistance is not constant. The resistance is not constant. Here, voltage by current, no matter where you go, it is the same. But here, in non-ohmic devices, the resistance is not constant. So, that is a major limitation. So, you should know about this. Okay. Lot of compounds are there, non-conductors are there, semiconductors are there, diodes, vacuum tubes, capacitors, all these things. Voltage is not linearly proportional. So, resistance is not constant. Only for them which are ohmic devices, resistance is voltage by current will be always true, and it will be a constant. So that is a limitation of Ohm's law. Keep that in mind. Yeah. Capacitors with resistors combination and capacitor combinations with each other, the tricks, Wheatstone's arrangement with capacitors, etc. That is remaining, like I mentioned in the chapter. We'll be doing it with current electricity when we do combination of resistors and all those things. Yeah, Sumit? Rama, if you ask me direct formula, direct questions will be very less. Out of 25 questions, it will be like barely 5 questions or something like that. Maximum 10 questions. Sometimes the questions could be using multiple formulas, not just one formula, 3 or 4 formulas together. Like we have solved many times, most of our questions, 2 or 3 formulas are there. So those kind of questions you can say are decent in number. So around 10 questions you can say to 12 questions which might be formula based. Okay, but multiple formulas. Single formulas are very rare, but maximum 5 if it is an easy paper, but usually 2 or 3 questions. Yeah. All right. Now that we know how Ohm's law is, we can now define something called as resistivity for that particular resistance. So if you have, let's say, a conductor, let's say this is the conductor having area A, it has some area A, length L, it can be converted into a resistor. It can be converted into a resistor of resistance R. So this is my conductor. This is the resistance of it. This resistance of that conductor has been found to be proportional to the length and inversely to the area. So to replace that proportionality with equality, we bring in a new guy, that is resistivity. This rho is called as resistivity. and this is a property of a material. So keep this in mind. If I take a big conductor, small conductor, resistance will change, but resistivity will not change. It's a property of a material. Resistance is not a property of a material alone. It depends on the length, area, etc. Wider area, less resistance. More length, more resistance. So if it is longer, it has more resistance to offer. If it is wider, then the charges have many options to flow from. So when the options are more, the resistance will decrease. So that's how you can think of it. So this is resistivity. This is basically resistivity. Now, if you ask me what is a unit, well, the unit of rho, which is resistivity, think about it. This resistance is nothing but ohm. This area is nothing but meter square, and that length will go down, becomes meter. So meter will cancel, so it will become ohm meter. Ohm meter. So you can also rewrite this like this. So it was ohm multiplied by meter square divided by meter. So it will be ohm meter. That is the unit of resistivity. That is the unit of resistivity. The inverse of resistivity is called conductivity. Conductivity means how conductive it is. Conductivity is inversely proportional to resistivity. Is inversely proportional to resistivity. The symbol for conductivity is sigma, and it is just simply the reciprocal of resistivity. That's all. It's just the reciprocal of resistivity, nothing more, nothing less. So if you ask me the unit of conductivity now, the unit of conductivity, well, I will say it will be ohm inverse meter inverse. So I can also comment that if it is a bad conductor of electricity, bad conductor of electricity, if it is something like a bad conductor of electricity, then resistivity will be very high and conductivity will be very, very less. But if it is a good conductor like silver, gold, copper, etc., if it is a good conductor of electricity, then I can say that the resistivity will be very less and the conductivity will be very high. Okay, so that's what resistivity and conductivity are for. All right, everybody clear till this point? Absolutely. Okay, so now let's see some questions based on this. Here it comes. Let's see. A uniform metallic wire carries a current of 2 amperes when battery's voltage is this much. The mass of the wire is this much, density is this much, and the resistivity is this much. The length of the wire is asked. Wow. See, they have played along with the variables. First of all, let's think current is given and voltage is given. So using voltage is equal to current into resistance. Resistance will be voltage by current. Voltage is known, current is known. Resistance, I don't know. But we know resistance is resistivity length by area. Somehow I can see that resistivity is given, length is asked, and area is not given. Okay, mass of the uniform wire is given and its density is given. Interesting. So the length is asked. So somehow can I write area in terms of volume, density, or something like that? I think so. See, density is mass by volume, and volume is area by length. Volume is area into length. So if I write what is area, area will be nothing but mass divided by density multiplied by length. Interesting. What if I substitute it over here? So first of all, this resistance over here is nothing but voltage by current. Resistance is voltage by current. I put it over here as it is. Resistivity, I don't know. Oh, sorry, I know, but I'll put it later on. Length, I don't know. Area, I will substitute from here. It is M by density multiplied by length. Oh, perfecto. I think I'm reaching closer and closer to my answer. Observe this now. So if I write it down properly, it will be voltage by current is equal to uh, you have your rho and divided by m, and that density will go on the top. Rho by m, d goes on the top, l also goes on the top. It will become just l square. It will just become l square. Perfect. Solving this, I should get the answer. So L square will be voltage by current into M divided by rho D. So therefore, L will be nothing but root of all those things. Root of all those things. Voltage is given 3.4. Mass of the wire is given, yeah, this much. What is it? 8.92 10 to the power minus 3 kg. Then current is also given, which is 2 amperes. Then resistivity is also given, which is 1.7 into 10 to the power minus 8. And lastly, the density is also given. Density is 8.92 into 10 to the power 3 into 10 to the power 3. Many things are getting cancelled, like 8.92, 8.92 and all of that. 2 into 1.7 is 3.4. Easily you can get the length to be around 10 meters. You can see many things are getting cancelled over here. Yeah, so length, you should get it 10 meters after solving. Is it clear, guys, how to solve this? So you can see this is a formula based question, but many formulas are there. First is Ohm's law formula. Second formula is resistance formula. Third formula is density formula. So from density, I got area, which I used here because area was not given. That's why you should think, why is density given? There is a reason why, because area was not given. So I substituted. Resistance, I got it from here. Solving this, I get L square. So L will be root of this. That's all. You should always tell that whenever you visit a VLC. Yes, I'm a Shreyas Sir student. Great. Okay. So all right, so this is done. Now let's do this particular question. Consider the four conducting materials: copper, tungsten, mercury and aluminum with resistivity this and this. Compare their resistivities. This is directly based on the concept which I just told you over here. Bad conductor versus good conductor. More resistivity versus less resistivity. So just use that concept, 100% you are going to get it. Yeah, just think about it. This is like more of general knowledge: copper versus tungsten versus mercury versus aluminum. Yeah, rho C for copper, rho T for tungsten, rho M for mercury, and rho A for aluminum. Think mercury is not that great conductor. Copper is the best, so it will have least resistivity. So A option is ruled out. Even it could be C, B, or D. So between aluminum and mercury, mercury will be a worse conductor. So D option gets ruled out. Between aluminum and tungsten, well, I'm not really sure, but I think tungsten is aluminum. I think might be a better conductor. Yes, so mercury is a bad conductor. Aluminum is a better conductor. Copper is the best conductor. So I think it should be B option. Just check it out. Yeah, B option. Yeah, perfect. All right, Rajesh, are you coming to Chennai? Chennai, I came and went, man. Sunday only I came and went. Yeah, I had messaged on my group, Telegram channel, Instagram, everywhere I had messaged. Hmm. Uh, yes, Rajesh, why not? Why not? Please let me know what help you need, and definitely I'll help you out. Okay. So mercury is a bad conductor, copper is a very good conductor. Between aluminum and tungsten, I think tungsten is a worse conductor than aluminum. You have aluminum wires. Tungsten has higher resistance because that's why it is used in some bulbs and all, heating coils and all of that. Yeah, so it has slightly higher resistance, definitely. So C option is ruled out. Okay, completely based on this. Now there are concepts on stretching of wire also, where the same wire is stretched, what happens to the resistance? So R is rho L by A. Lot of people think if length increases, resistance increases directly. That is wrong. So when a wire is stretched, what happens is the volume remains the same. The volume is going to be the same. So volume being area multiplied by length, I can easily say that the area is volume divided by length. So area is nothing but volume divided by length. So if I substitute that over here, rho L is whenever you stretch a wire, the volume will remain constant. So area into length, which is volume. So area will be volume by length. So if you substitute it in the formula of resistance, V by L, that L will multiply on the top as L square. So resistance is proportional to the square of the length, not directly proportional to the length, only in the case of stretching and compressing of wires. Okay? All right, perfect. So, talking about this previous year question, the wire of resistance is drawn out so that its length is increased by twice of its length. Okay, so this is the question directly based on this particular concept. Same concept. So, let's see if you can solve this. Earlier, imagine the wire had some length. It has been increased by double of its length, meaning lot of people think the length has been made 2L. That is one another mistake. Read the question. The length is increased by twice of its length. So it has been increased by, this is that increased by double of its length. So the actual length will become 3L. So original length was L. It is not increased to. If it was increased to 2L, then the total length will be 2L. If it is increased by something, then original length plus something. It is increased by an amount. My weight is 70 kg. I increase my weight by 20 kg. By 20 kg, I increase my weight means my final weight is not 20 kg. It is 70 plus 20. Got it? So a lot of students make this mistake. So resistance being directly proportional to L square. So R1 by R2 will be L square by 3L square. So this will be nothing but 1 by 9. But this is nothing but old by new resistance. The question says new resistance to original resistance. So R new by R old will be 9:1, which is option number A. Those students who will commit a mistake, they will say 4:1 because many people will think it is 2L and 2 square is 4. Many people will make that mistake. Now that we have understood resistance, it's good time we go back to our questions which we had left over here. And I told you, I will solve it for you over here. For example, this one, here, yeah, over here. Notice over here, what will happen is, in this particular question, the voltage was the same, okay, the voltage was the same, but what happens to the drift speed was asked. So I have an idea that the current will change because the resistance would have changed. So looking at current is voltage by resistance, and resistance is rho L by A. So V A divided by rho L. As you can see, that resistivity will not change. It's the same material. Voltage is the same. Length is the same. Area has changed. So if the area has been made 2 times, it's obvious that the current is also made 2 times. So if the current also has to change, 2 times, can you notice both in the LHS and in the RHS? LHS increased 2 times, RHS increased 2 times. So the drift speed has no reason to change. So that's why it will remain the same. And hence the answer for this will be VD only. It will be just VD. That's it. It will not change. It's a beautiful question because a lot of students usually think the area is doubled, drift speed will become half, but they forget current will also change. So current is voltage by resistance. Resistance is rho L by A. Area doubled, so current will also double. Hence, cancelling on both sides, drift speed should remain the same. What a beautiful question. Yeah. Yeah. In this question, it is not based on stretching. It's a new wire of double the cross section of the same material. It's not that the wire has been stretched. Yeah, be careful. It's not stretching of the wire. It's a new wire of the same material. There is a difference. All right, sir. Sir, this is amazing. Sir, there was one more question. We'll come to that. But before going ahead, I wanted to talk about temperature dependence also. This is also very important. That resistance also changes with temperature, usually linearly. So for small changes, small to moderate changes, the resistance at any temperature T is given by original resistance R naught 1 plus alpha into change of temperature. This over here is our new resistance. This is original resistance. This delta T is the change in our temperature, and this alpha is called coefficient of thermal resistance. Coefficient of thermal resistance. This tells me how sensitive my material is for resistance, for temperature, sorry. If I change the temperature by a degree, the resistance changes by a lot. Alpha is high. It changed the temperature too much also. Still the resistance is not changing. Then alpha is very small. So alpha defines like the sensitivity of the resistance towards the temperature, fluctuation of temperature. Today it is hot, tomorrow it is cold. Resistance is like I'm still same only. Alpha is very low. Resistance is changing huge. Even if there is small variation in temperature, then alpha is very, very large. So keep this in mind. Okay. So this is the formula. Now also notice alpha is positive for conductors. Positive for conductors, meaning when temperature increases, resistance increases, relaxation time decreases. It kind of makes sense. When temperature increases, the electrons are more mobile, more thermal energy, they collide more frequently, so they are not getting enough time to relax, and because of which they face more resistance. But in the chapter of semiconductors, you will say alpha is negative for semiconductors. The reasoning will be told later on why it happens. It is because of band theory. So for semiconductors, when the temperature increases, the resistance decreases. So that's why alpha is negative for semiconductors. This is very important. This has been asked in the previous years as a direct statement based, theory based assertion reason, or statement 1 is true, statement 2 is false, those kind of questions. Okay, you will see it many times. Please keep this in mind. Is this clear? Okay, semiconductor reasoning we'll be doing later on, but for now just remember, for conductors, more temperature means the molecules are moving at higher speed. They will collide more frequently. They were colliding after 2 seconds, now they are colliding in half a second. So if they collide more frequently, they experience more resistance. So current will reduce, so resistance will increase. That's what the logic says. Okay, now the last one over here, resistance and resistivity. By our Ohm's law, we saw voltage is current into resistance. Therefore, voltage is current into resistance being rho L divided by A. Let's start shifting the terms. I will write length over here and I will place area below the current, leaving resistivity as it is. Voltage per unit length. Voltage per unit length. What is it? It is electric field. Current per unit area is current density. This is rho. So E is equal to J rho or rho J. So in the vector form, electric field is resistivity into current density. This is vectors. So this is also a very, very important formula. This is also a very, very important formula. E is rho J. E is nothing but rho J. Thank you so much. Yeah, ray optics will come later on. Ray optics will come later on. Okay, Fanny, thank you so much for loving the classes. This formula As you can see, we can use it over here. When we did this particular problem, where did it go? This one. The cross section was changing, current was same, current density was different, drift speed was different. What about electric field? Well, think about it. E is rho J. E is rho J. Rho is the same material. Okay, this particular thing is same material. J has obviously changed. So J, when it decreases, even electric field should decrease. So same logic like J. So if J is less, so here also electric field will be less. Okay, E is a rho J. Resistivity is a material property. It doesn't matter whether area is more or less. All right. What about mobility? Now for that, we can use this. Mobility is nothing but your drift speed by your electric field. As you can see from here to here, electric field has reduced and drift speed has also reduced. Both will reduce by the same amount. So mu will not change, and that's why it will be equal. In fact, that was also the reason why in this particular question, the answer was C. Even if field changes, drift speed will change accordingly, but mobility is the same for a given material. So it will be independent of the electric field, and that is also what we are being able to reason out even in this problem. Just because the cross section changes doesn't mean the mobility will change, it will remain the same. Beautiful concept, beautiful question, loved it. Yeah, everyone? Great. Moving ahead. All right. So E is rho J. We can also play around with these equations a little bit more to get anything else. Like for example, E was rho J. E is rho into J. So somebody will be like, sir, I want to take a rho over here. Fine. And 1 by rho is equal into E is equal to J. 1 by rho is conductivity. So conductivity into electric field is J. But wait a minute. I also know what J is from this formula, drift speed formula. Check this out. J was NVD. J was NVDE. Yeah. So why not put it over here? So J was NVDE. Where is it? Yeah. J was nothing but NVDE. But wait a minute. I also know the formula for drift speed. It was E by M. Yeah. And this E is as it is. So this E and this E will cancel. Can you see that over here? This electric field and this electric field will cancel. And I will get conductivity as N. Oh, sorry, there was tau also. My bad. E by M into tau. So N into E square tau divided by M. This is also a formula which sometimes can be useful. But as you can see, you can derive it very easily using these other formulas. So conductivity is Ne squared tau by M. So temperature, if relaxation time reduces, conductivity reduces. Kind of makes sense. Yeah. If thermal energy increases, relaxation time will reduce, it will become less conductive. Relaxation time is more, it becomes more conductive. So Ne squared tau by M is the formula. Okay, sir. Perfecto. Let's do some questions then on this. Where did it go? This one. Yeah. The current of 5 amperes is passing through a non-linear magnesium wire. At every point, the direction of the current density is at an angle of 60 degrees with the unit vector of the area. The magnitude of the field at every point of the conductor is how much? Resistivity is given. So, as clearly mentioned over here, at every point, the direction of the current density is making an angle of how much? Is making an angle of 60 degrees with the unit vector of the area. Okay, with the area's unit vector. Okay, with the unit vector of the area. Okay, the magnitude of the electric field at every point of the conductor is how much? Okay, fair enough. Let's see what we can do over here. We want to find electric field. If we are knowing the resistivity, we know one thing. E is rho J. E is nothing but rho into J. So if E has to be found, I need to know the resistivity, which is already given. I just need to know the value of J. But how much is J? That is not given. Fine. So let's think. If I want to find J, I know current is J dot area vector. Current is J dot area vector. Now, 5 amperes of current is passing through a non-linear magnesium wire, cross section of 0.04 meter square. Okay. As you can see, current is given, which is 5 ampere. J, I don't know. Area is 0.04 and dot product means it is JA cos theta. So I can put cos of 60 degrees over here because it makes 60 degrees with a unit vector. Also, it will make the same angle with the actual area vector. All right. So from this, J will be 5 divided by 0.04. Cos 60 was half. So it goes as 2 over here. So this will be 5 2s are 10. 4 is 0.04 is 4 into 10 to the power minus 2. So this will just become J as 5 by 2 into 10 to the power 2 ampere per meter square. So substitute that over here. J is nothing but 5 by 2 into 10 to the power 2 ampere per meter square. And other thing, resistivity is 44 into 10 to the power minus 8. All right. So that will be electric field. That will be your electric field. Now 44 goes with 2, 22 times. Yeah. 22 into 5 is basically, 110. And this and this will make it 10 to the power minus 6. So can we write this as E is 11 into 10 to the power minus 5 volts per meter. 11 into 12 to the power minus 5 volts per meter. That is the correct answer. Perfect. We got it. This was asked in the previous years. Yep. No, it is not option C. It is option number A. If you have missed some of the powers, then you might have got option C. But if you don't miss powers, it will be option number A, minus 5. That was the question. Okay. Yeah, that was the last question. I've already given you the homework. Please solve it. So you have completed all the parameters, be it current, current density, field, relationship with resistivity, conductivity, resistance, how temperature affects, relaxation time, everything in this particular class. It's a power packed class. I know a lot of things you might be jumbled up, but when you practice more questions from Tattva books, from the PYQs, you will get more and more confidence. Please revise these formulas. Direct questions do come from these, concepts which I have taught today. And current electricity is a heavyweight chapter. So make sure you're solving enough number of questions. Okay. So I want to see everybody solving the homework question down in the comment section, and PDF will be there soon by tomorrow. All the best, and do not forget to like and share and subscribe to the channel. This was your Captain Shreyas. Have a great night. Bye bye. Take care.